without further ado, let me move to introduce our third plenary speaker today. It's really a pleasure to introduce Professor Richard Baraniuk. He's the Victor Cameron Professor in Electrical and Computer Engineering at Rice. Rich really has a very long and beautiful series of contributions in both theory and algorithms, but also in hardware, in sensing, signal processing, machine learning. He's a fellow of the American Academy of Arts and Sciences, the National Academy of Inventors, the American Association for the Advancement of Sciences, and the IEEE. He's received numerous awards, including the DoD Faculty Fellow Award and many other awards from the IEEE. Let me also mention that Rich is the founding director of OpenStack, which is a nonprofit that works to facilitate means for education basically everywhere. And so it publishes openly licensed college textbooks that are made available for free online. So Rich, thank you so much for joining us. It's really a pleasure to have you here and tell us about Affine Splines.
Thank you. Can you hear me okay?
We can hear you fine.
Perfect. Okay, it's great to be here. I just thanks so much for all the organization of putting this meeting together. It's been so disappointing we couldn't all be together in person, hanging out, so many good friends. But I look forward to hopefully next year's Deep Math meeting, we'll be able to be in person. I'm just really looking forward to it. So what I'd like to talk briefly about today is some work that we have been doing on trying to understand what goes on inside deep networks. Hopefully there'll be something in this talk for everyone, and both from a theory side of things, but also from potentially some aspects that could be practically useful. So let's jump in. So let me get there we go. There we go. So we're here today because we're interested in solving prediction problems. Basically trying to make an inference or approximation of some prediction function f, and learning it from data. And the theme of this meeting is that we're looking at various deep learning approaches to solving these kind of prediction problems from data. And the thing that's really interesting about deep network-based prediction is the hierarchical aspect, the fact that we process our data through multiple layers, which corresponds to applying a composition of operators to our input signal, right? And I can actually state right up front here the challenge that we're trying to attack in my group in particular is the fact that deep nets are just so easy to describe locally, right? We can solve data with filters and learn the parameters. We threshold with scalar thresholding. We subsample. These are so simple to describe, but it's not clear at all what is actually happening once you start chaining these simple operations together. And not a lot of progress has been made on describing the global structure of this transformation that's made from the input to, say, the output of a deep network. And because of this, work has really progressed empirically, right? And because it's so difficult to describe the global transformation, and we have pretty much treated networks as black boxes with zillions of parameters. And well, this is a very powerful approach, powerful enough to lead some of us to think that, maybe deep nets are taking us to some higher intellectual plane. Maybe. I would argue that they remain, inscrutable and mysterious. And so we're really trying to understand what's going on inside there. Okay, so and our particular approach, along with numerous other teams around the world, is to look at the spline approximation aspects of deep nets. And so that's what I'm going to talk about today. And like I just said, there are a number of folks working on this, and we've been discussing and collaborating with a bunch of them. So the bottom line is that deep nets solve prediction problems, not just hierarchically, but using a very special family of splines that we're going to talk about briefly. Let's just super quickly review, just to get everybody on the same page, what I mean by an affine spline approximation. So let's say that we want to approximate this nice blue, smooth blue curve here. Well, then a spline approximation consists of two aspects. The first aspect is that we partition the independent variable, right? In this case, it's just the one-dimensional x-axis, right? But in a deep net, it might be a 10,000, 100,000 dimensional image, let's say. And so we partition the independent variable, the input space, and then on each of the partition regions, here we've cut our independent variable into 4 separate regions, and then on each region, we simply fit a affine or linear operator, right? Potentially also with the requirement that the hooking these together, the overall local affine operator stays continuous. Okay, so there's the partitioning and the local mapping, and there are 2 ways to approach spline approximation. The first is the really powerful way. This is where you leave the partition unconstrained. This is so-called free knot splines in one dimension. And then you're unfortunately, though, faced with the difficult problem of optimizing both the partition of the input space and the local mappings. And this is a highly nonlinear, completely intractable problem. Even in one dimension, this is very, very difficult. And in high dimensions, it's hard to even pose this problem. So that's the powerful approach. The other approach is the easy approach, where you either fix the partition, where you fix it using, say, a regular grid or a dyadic grid. That's what gives wavelets. And then you only need to optimize the local mappings. And so what we're going to see is that deep nets allow us to basically to do an approximation of the more powerful free knot spline approximation case in extremely high dimensions. And that, I think, is something that's really interesting. So I'm going to pose everything in this talk according to a particular way of looking at splines in deep nets. It's not the only way, but it's just a particularly attractive way for setting everything up. And this is the max-affine spline viewpoint that came out about 10 or so years ago. And so the basic idea of a max-affine spline is we want to form a continuous piecewise affine approximation of a convex function using R regions, carving the input space up into R regions. And so if there's R regions, there are going to be R affine functions, right? One for each of the regions. So little r here goes from 1 to capital R. And for each little r, we have a set of slopes in this A, and we have a set of biases, or a bias if it's in 1D, in this B parameter, right? And let's just look at a set of these. Let's say that R was 4. We're in one dimension to keep everything simple. And so that means we'll have 4 sets of A's and B's, A1, B1, all the way through A4, B4, slopes and y-intercepts, right? So now what the max-affine spline sort of framework says is that if you're going to approximate a convex function over using these R affine functions, then it's actually very easy to find not only the approximation, but also the partitioning. Basically, what you do is you just take the spline approximation is formed by taking the maximum of each of the set of these, in this case, 4 straight lines, and that is going to form our convex approximation. So let's just look in this particular space, part of the input space. We see that there are 4 red lines crossing through this space. This is the one corresponding to A1, B1 that lies highest above all the others. And so that is the one that is active in this approximation, right? Then you see that it crosses line corresponding to A2, B2, and that is precisely where we switch from one partition region into the other, right? So very, very simple setup in one or in many dimensions. And the critical thing that I just want to make clear to everybody is that there's a really nice connection between the spline parameters, the A's and B's, and the partition. In particular, if you fix a set of A's and B's, okay, then that automatically implicitly defines a partition, right? Because once you fix the A's and B's, you have these functions, and then you know that wherever these functions cross and where one higher function switches to become not the highest function, that is exactly where the partition boundary is. Okay, so there's this really nice sort of yin-yang connection between the parameters and the partition. So let me try to convince you that this is interesting for deep nets. So let's start with a trivial example, and that is, what if we take a one-dimensional variable x, we scale it by a, that's kind of like a matrix multiplication by a, add a bias b, and then pipe it through a ReLU. Well, it turns out if you just write out what that corresponds to, it is in fact a max-affine spline with r equals 2, where a1, b1 is just 0, 0, and then the other spline parameters are a2 and b2. Okay, so this corresponds to the following, not necessarily impressive spline approximation of this convex function, but the really important point is that given this fixed a, the A's and the B's now, it is very easy to find the partition from where these functions cross. Okay, so that's a max-affine spline in one dimension. You form an operator in higher dimensions, meaning an operator that will map not just a vector input in d-dimensional space to a single number, that would be a spline function. We can form a spline operator by just stacking k of these spline functions into to form a capital K dimensional output, and we call that a MASO, or a max-affine spline operator. Okay, so that's all the setup. So if we focus like most folks are these days, both on the theory side and also the practice side, on deep nets built from piecewise affine layers. So this would be any layer built from fully connected matrix multiplies, convolutions, adding bias, leaky ReLU, absolute value, activation functions, max, mean, channel pooling. All of these operators turn out to be piecewise affine, max-affine spline operators. So we can state a theorem, pretty simple to show, but a key result for us is that the layers of a modern deep net, just about every architecture we've ever looked at, they can be the individual layers can be written as MASOs. Okay, so in this case, these three layers of this deep net, each of them is a max-affine spline operator, and this is nice because it means we know a lot about not only the spline mappings, but the spline partition function. We'll come up with that in a minute. And also, each of these is a convex operator with respect to its input space. Okay, so that's individual layers. And of course, we're not interested in just individual layers, that's the local understanding of a deep net. We're interested in what goes on globally. Well, when we concatenate any more than for two or more of these max-affine spline operators, we lose this max-affine property, but the overall mapping from, say, the input of this deep net to, say, the output of the third layer or the output of the entire network, it's a composition of max-affine spline operators, and it's going to be a non-convex but continuous piecewise spline operator. And people might know the term CPA, or continuous piecewise affine approximation, that comes from splines and from control theory. Okay, so this is where things actually get interesting, right? It's not just the spline mappings that are interesting, but it's the partitioning of the input space that we are really interested in. Okay, and in particular, studying the geometry of that input space. And again, let's just go back to what we talked about a few minutes ago, and that is that the the parameters of a deep network layer, right? One layer of a deep net, induce a partition of that layer's input space with convex regions. And again, it's basically the same idea that once you fix the parameters of the deep net, it's just as though the A1s through B4, A1, B1 through A1, A4, B4 of this simple example drawn down here are fixed. And that means that we can just find by finding the intersections of these lines in 1D, there'll be hyperplanes in higher D, we immediately can obtain the partition of the input space, okay, which is something that we're really interested in studying, right? And moreover, we're not going to study the partitioning of just one layer of a deep net, but the partitioning induced by a composition of several layers. Thing is that there are some really neat connections between this idea of partitioning of the input space into, what we would call spline partition regions. Other people just call linear regions. Deep links with things that are very familiar from information theory, statistics, and computational geometry. Ideas like vector quantization, k-means, Voronoi tilings. In fact, deep network is just a massive vector quantization machine, and that's something that we're going to be talking a little bit about later. So in order to make this all concrete, let's do just a quick case study. Very simple deep network, a 3-layer deep net with a 2-dimensional input space so that we can actually visualize the input space, a 4-dimensional output space because we're going to be interested in a 4-class classification problem, and then 2 hidden layers in between, one 45-dimensional and one 3D. Okay, so this is our layer, our architecture. Here's the input. It's a 2-dimensional input, and so we can draw it in 2 dimensions with an x1 and an x2 axis. The 4 classes correspond to the green, red, blue, and cyan X's here, the data points, and we use standard learning methods to learn the parameters of all of these 3 different fully connected layers from the input through to the output. Okay, so now this is the representation of the input or the training data. And now let's look at what happens in the very first mapping from the input of our deep net through to the output of the first layer. Okay, and what we get is a partition that looks like this. You see that we have what look like a bunch of transposed or translated cones that break up the input space. Again, how did we figure out where these regions lie? Well, it's simply by in this case numerically figuring out where these hyperplanes, right, are crossing. Note that these regions are all convex, yeah, so this is the and so a deep net is basically breaking up this input space into these regions, and then it is fitting a separate affine mapping, just affine transformation on each of these regions. So when we think about an input falling into a particular tile down here in the lower right, well, our input X fell into that tile. And so there's a mapping from that tile, we'll call Q of X, that allows us to go look up in a library of affine transformations that are stored, one transformation for each tile. And so given an input X, we see that the output of this first layer, Z, will just be a particular matrix that lives up in this library indexed by Q of X, and a particular vector B, again, pulled out of that library. So Q of X is this indication, this lookup function, right? So that's what goes on in one layer. Now, if we ask what goes on when we have 2 layers, when we think about the mapping from the input to the output of the second layer, well, we're still going to have convex regions. We're going to talk more about this in a couple minutes. The regions here might not look convex, and that's only because of aliasing artifacts. Randall, who did all of the thinking and doing for this, really wants me to replace this picture, but I really like it's evocative of what's going on. So you should just remember that there's some aliasing artifacts that make these regions maybe not look convex. But again, given an input X that falls into this particular region in the bottom right again, there will be, again, an operator Q that will map that input X to a library where we can look up an A and a B that now correspond to a affine transformation input to the output of the second layer. Okay, and so for any arbitrary place that you want to go in the network, there will be a vector quantization tiling, right? One of these partitionings, and then just simple and affine transformation that maps the input to the particular point you're interested in terms of an X and a B vector. And when we learn a deep net, what we're doing is we're really adapting this this vector quantization or this spline partition set of regions so that over time we get something that is more adapted to data manifolds on which our data lie, right? So let's talk about some of that's just really a bunch of identifications of what's going on in a deep net and connecting to this idea of max-affine splines and the affine transformations that live over each of these partition regions. Let's look at what we can do, right, with this this particular viewpoint. And we're particularly interested in the geometry of what's going on in a max-affine spline. So the first thing we can say that's pretty interesting is that the partition of a layer, one layer, which is a max-affine spline operator, from its input to its output. For example, convolution followed by adding a bias and then going through a ReLU. Actually, that partition isn't a Voronoi tiling, actually. It's a more general tiling called a power diagram, right? What is a power diagram? A power diagram is a generalization of a Voronoi tiling where you have a set of centroids, right? Just like in a Voronoi tiling, but you also have what's called a radius parameter that for each of these centroids that warps the geometry of this Voronoi tiling to change where the various cuts happen in the high dimensional input space. However, and you can view this two parameter having a setup where you have both a centroid and a radius as using basically building up a Voronoi tiling, but instead of using Euclidean distance to assign points in the space to a particular tile, you use what's called a Legendre distance, right? So that's another way of looking at it. No matter how you interpret this tiling, because we know we have a power diagram, we know that we are cutting the input space into a set of convex polytopes. Moreover, we actually have formulas, right? Formulas for the centroids of these various tiles and these radii parameters in terms of these mappings that we talked about earlier. So you actually have formulas for these A's and the B's, and that gives us closed form formulas for the centroids and the radii. Okay, so when we go through multiple layers, composition of MASO layers, well, it turns out that we still have a power diagram. Let's say you go through 3 layers in a deep net, but now it's easy you can show that this power diagram is built up by a very interesting subdivision process. And that subdivision process might make you start to think ideas like quad tree approximation or wavelets or fractals. And it turns out we can actually characterize what goes on in this subdivision process. Each layer, right, will make a number of hyperplane cuts in the input space, but only the first layer will make straight line cuts, straight hyperplane cuts. The cuts caused by subsequent layers will actually be bent according to the A and the B parameters of the earlier earlier layers. So here's just a simple picture of what's going on. Say again, we have a two-dimensional input space, and we go through this red layer here. Well, it might induce 6 cuts in this input space, and again, the convex polytopes that are defined by these cuts as boundaries will not only be convex, but the affine mappings, as we move from one partition region to the next, will stay continuous, right? So we have a mapping from the input to the output of the second space. Now, if we go through this, not only the first layer, but also a second layer, and we think of what the impact is of that second layer on the input space, well, it turns out that you can draw the power diagram of the combination of the first and second layers as follows. All of the cuts that were made by the first layer remain. They're colored in gray here. And now the cuts that are induced by just the second layer will be bent, right? And they're going to be bent by the corresponding to the learned values of the A and B affine transformations in each of these regions, right? So you can actually characterize this bending, okay? And we can say quite a bit about this this subdivision process, and it's through this subdivision process that we can see that this is why a deep net is a really practical and efficient way for doing some kind of high dimensional hierarchical free knot spline approximation, right? And that I think is the thing that, to me at least, is most interesting about deep networks, is that they make high dimensional free knot spline approximation practical. Moreover, you can think about, say, in a classification problem, what the class decision boundary might look like. Well, that is, again, merely just a cut in this final layer of the deep network. And so again, we can study that, how that straight line hyperplane or straight hyperplane is actually bent according to the affine transformations at earlier layers. And it turns out that we can actually say a lot about the dihedral angles of this bending. And if you know about the angles of that bending, that allows you to say something about the regularity of the boundary. How smooth is it, right? Where is it bending a lot very quickly? Where is it bending not a lot, right? So there's some hope here to be able to actually characterize what goes on in the final decision boundary of a deep net by studying this subdivision process up through all of the layers in a deep net. Just put in a little advertising for a really cool app that Randall has developed that is going to be up on the web soon, that will allow you to build an architecture or choose from a library of architectures and actually explore, right, how these various nodes, right, or neurons within a deep net induce certain boundaries, right, decision boundaries, not decision boundaries, spline partition boundaries in the deep net, depending on whether you're looking here, for example, at the first layer, or what's going on here at the second layer. And so that's something that folks should be able to play around with in the very near future. So let's look at in a little bit more detail. We talked about geometry of the partition. Let's talk a little bit about the mappings on each partition. And it turns out they have a very nice interpretation. Let's think about, for example, the mapping from the input to all the way to the output, which would be, we could call it ZL if it's an L layer deep network. Let's look a little bit into these affine mappings. Well, again, given an input X, the mapping, from the input to the output of this network, it will be defined as simply an affine transformation, right? Where again, given X, Q of X looks up the particular A and the B from some library. We actually have formulas for these A's and the B's. So if you know the parameters of the matrices for convolution are fully connected that you've learned, and then the parameters of your activation functions and pooling functions. You can actually just build up these A's, right? The A's and the B's. And now we can ask, this is a simple question, that given the mapping from this input to this output, okay, the classification network, right? So the output is going to be like, if we ignore the softmax at the output, which we can do without loss of generality, this output is going to be like an unnormalized histogram, right, over the different classes of the classification problem, and you're going to be picking the biggest one, right? In this case, turns out boat will be mapped by softmax to a probability of 0.94, right? And that's the biggest one, and that's why you're going to classify this image as a boat image. That's so the important thing is here is that you are running your input through an affine transformation, an A matrix multiplied by X. How many rows does this A matrix have? It'll have 4 rows because it's a 4-way classification problem. Okay, well, how do we get the output vector, which is 4-dimensional? We take each row of this A matrix and we multiply it by X. Okay, plus we add a bias. Well, what is going on here? That's an inner product, right, of a row and a signal. And we're going to do that 4 times, 1 for each row, and we're going to take the biggest. Well, what is this? It's a match filter bank, right? Nothing different than a match filter bank that's been around for 70, 80 years. Basically, we have in this A matrix a number of rows equal to the number of classes. Each of these rows we call a match filter. We're going to take a simple linear inner product of our input image with that row, and the biggest one wins. Okay, so this is standard thing from radar, sonar, etc., and is actually optimal for signals in additive white noise, white Gaussian noise scenarios. And so this lets us give a theoretical interpretation of what folks have called saliency maps, right? That basically these rows of this A matrix, we can actually calculate them, and they are match filters for a particular classification problem. Here's this quick example from CFAR 10. Input is an airplane image. We see that the row of the A matrix corresponding to airplane class, if you squint, it kind of looks airplane-like. Ship and dog classes, those rows, they don't look ship-like or dog-like. They're actually trying hard to be anti-airplanes, right? And these are the inner products between these templates, right? And match filter templates and this input image. And you see that plane is the one that maximizes. So you can interpret a deep net as a matched filter, right? A matched filter bank that is applied to your input, where that matched filter bank is adapted or changed for each of the different vector quantization tiles or power diagram tiles in your overall spline mapping, right? So hopefully that is a useful interpretation. We can continue with this connection with VQ and Vorent power diagram tilings. Now, if you think about three different inputs in the input space, well, each of them has a mapping, right? Q1, QX1, QX2, QX3, and these mappings Q, again, we've thought of them as a lookup function for a particular A matrix and a B offset vector, right, in some library. But we can also think of this Q of X as a code, right? And in fact, if you use, for example, a ReLU activation function, you can actually make a one-to-one correspondence between the lexicographical ordering of the on and off state of the ReLUs in a network, meaning whether when you put a certain input in, whether a ReLU is turned on, meaning passes through the value that was the input, or zero, or the the zero value when you threshold the value to 0. This gives you ones and zeros. A lexicographical ordering of that gives you a code word. And now you can actually look at the code word distance or Hamming distance between these strings of 0 and 1s. And that lets us compute a new kind of distance, right? A distance where the Hamming distance between the zeros and ones of these adjoining tiles will actually be small. And the distance from tiles where we had to go through many different tiles, transit through many tiles in order to go from, say, the red input to the green input, will have a larger Hamming distance. Okay, and there's lots of things that you can talk about both empirically and theoretically in this setup. It turns out that empirically, we've been able to show through a number of different studies that the VQ distance between different, let's say, images on an image manifold, let's say if we're trying to classify whether a picture is of Anna or of Ingrid, it turns out that if you have two Anna images and you look at this VQ Hamming distance between those two images, that you can make a link between that Hamming distance and the actual geodesic distance along that image manifold that contains the various images of Anna were sampled. And so this is an area we haven't been able to make a huge amount of analytical progress, like proving theorems about this, but we have been able to make quite a bit of empirical progress, not only for image like particular for recurrent neural nets, which our theory also covers. So this is an interesting direction that we continue to push towards. Another is looking at deep generative models. So now instead of looking at deep networks that start from a high dimensional image and then collapse to a low dimensional regression result or empirical histogram, we're looking at starting from a small dimension, say just a Gaussian random vector, and then going through a deep net that's expanding dimension as we go through more and more layers. And if you're interested in probabilistic deep generative models, then what you're trying to do is map a simple probability density, like say a unit IID Gaussian low dimensional density. You're trying to map it up onto into high dimensional space where we have a probability density that lives near a manifold in this high dimensional space, right? So this is a very useful problem that has been attacked from numerous different angles. When you're trying to do not a deterministic but probabilistic approach, it turns out that because there's no access to date to the closed form formulas for the generated distribution or the likelihoods, you have to resort to various approximations. And the typical approach to date has been use a VAE, variational autoencoder type approach. Works pretty well, but the approximations are extremely crude. Okay, so we've been able to make some progress in this direction by exploiting the fact that a deep generative model is a composition of max-affine spline operators. That is, if it's using, say, leaky ReLU activations. We can, given a network, we can know a lot about its partition of this, the input probability space. And moreover, what this partition of the input probability space, what the deep net does is it maps it up to a manifold, right? A low dimensional manifold in the high dimensional space on which the moving around randomly in this unit Gaussian, in this low dimensional probability space at the input maps us to a probability in this high dimensional space. And using some really nice results about probabilities, calculating probabilities when you have polytopes in high dimensional spaces, we can actually get analytical expression for the posterior and for all the likelihoods that you need in order to not do the coarse approximations you have in a VAE, but actually do an analytical EM algorithm for learning. So actually do the right thing. So you have gradient-free learning that is guaranteed to converge locally, right? So that's something we think is kind of cool, that we can actually derive this algorithm. But even more importantly, it works really well. So let me just illustrate in a low dimensional example that will really highlight, so you can both visualize, but also so that it highlights the problems that VAEs face when their dimensionality is too small. So here's an example of a one-dimensional input latent space. So the input space here is just a one-dimensional Gaussian, and where we're interested in mapping, in this case, to a two-dimensional, a one-dimensional manifold in a two-dimensional space, and we're constraining the latent space of the network to be one-dimensional. That's very low, and you can see that the VAE is not able to learn very accurately this bell-shaped curve aspect of, or this smooth quadratic aspect of our data, whereas the deep generative model based on this MASO approach and empirical analytical EM algorithm is actually able to learn really quite accurately, right? Even just with a one-dimensional latent space, which it should be able to, but that VAE, its approximation is just too coarse. Here's another example of EM and VAE learning with the MNIST data set, again, with a very low dimensional latent space, okay? If you learned a VAE with a much higher dimensional latent space, it would look great, okay? But the idea here is to just showcase that if you have access to all of the analytical expressions, you can not only learn gradient-free, but you can also learn, really accurately. So what about beyond piecewise affine activations? ReLU might be all the rage today, but maybe someday we'll go back to sigmoid, right? And if you go to recurrent neural nets, activations like hyperbolic tan and sigmoid remain very important. So it turns out if you want to all the theory that we've talked about, if you have a piecewise affine activation, you can map all of this max-affine spline operator framework into recurrent neural nets. We've had some pretty good success doing that, actually being able to figure out that the typical initialization of recurrent networks, which is to set the hidden states to 0, is a really bad idea. And instead, you should use random initialization that naturally gives you an implicit Tikhonov regularization of the affine maps in your recurrent net. But that's for ReLU deep nets, or ReLU recurrent nets, that people are starting to migrate towards, but they're still not the main thing that people are using. So to look at sigmoid and tan-H type nonlinearities, it turns out that we can actually bring those into this theory, and not by approximation, right? Approximating a sigmoid with a bunch of piecewise linear pieces. We could do that, but that's not that elegant. It turns out the elegant approach is to move from what's called what everything we've been doing up to now, which you can view as a hard vector quantization. What do I mean by that? What I mean is that if X, the signal X falls into this tile, it is in this tile. Okay, it's a hard vector quantization. Moving to what is called a soft vector quantization, where if X happens to live in this particular spot of the input space, we say that it lives in this particular tile with high probability. It could also live in this tile with a sort of medium probability, and in this tile with a very low probability. Okay, a natural way to set that up is with a Gaussian mixture model over these tiles. And it turns out if you do that, you get a menagerie of infinite class of activation functions that correspond all along the along the continuum between with hard VQ at one end and soft VQ at the other end. So these are just some of the activations. And just a really interesting thing is not only is sigmoid gated non-linear unit along this, but also a nonlinearity that was shown empirically to outperform ReLU in a lot of classification experiments, called the swish nonlinearity. Okay, and it turns to also live along this continuum. In fact, it lives halfway in between, right, hard and soft VQ. So that's just kind of an interesting observation. Okay, so I think it's time to wrap up, right? What's the punchline? What we're trying to do is use this idea of a spline mapping and spline partitioning, in particular this max-affine spline partitioning, in order to provide a foundation on which we can build a theory of deep learning that will allow us to understand some aspects of what's going on globally within a deep net rather than just locally. We think there's some compelling ideas. The VQ dependent affine mapping, this relationship with or link with power diagrams and subdivision, this relationship or linkage with match filter banks and with data manifolds. And we think that we've really just scratched the surface of understanding what goes on globally in a deep net using these approaches. And there's just a lot more work to be done. Just like Renee is leading a big new NSF Simons initiative on deep nets. We at Rice are leading an ONR Muri that was funded this year with a number of folks that I'm sure you know that are interested in not only the representational aspects of deep nets, like Ron DeVore with splines, but also looking deeply into the optimization aspects and the statistical and formal characterization and verification aspects. So feel free to go to our website, deepmuri.rice.edu, where we'll be posting papers as we make progress, talks, etc. So with that, I'll end and say thanks so much again for the invite, and happy to answer any questions if there is time. I also realize I'm between everybody and the cocktail hour. So thanks a lot.
Thank you so much, Rich. That was awesome. Luckily, some people might have helped themselves for their cocktail hours in their respective time zones.
I'm having cocktail from my OpenStax mug, so feel free to check out openstax.org.
Excellent. We do have a series of interesting questions, and there's actually an interesting discussion in the chat. The discussion is around the number of partitions. So in particular, one of the questions is, how quickly does the number of partition regions grow with the number of affine constraints as defined by the intersection of the affine constraints?
Great question.
Could that become prohibitive?
Great question. So, and I guess I don't know if I can access the chat. I have to stop sharing. Let me stop sharing. Great question. Let me just say, well, yeah. So the answer is that the number of partition regions grows extraordinarily fast, right? So basically exponentially fast with the number of units in your network, and so there are literally zillions of these partition regions. Okay, so that seems like it might be a theoretical setback. With that said, though, there's some really interesting observations you can make. The first is that nearly all of these regions will be empty, right? Because you have huge numbers of regions, but most are going to be empty. And they're empty by virtue of the fact, and this is where I would really say you have this trade-off between local representation and global representation. The global so on the local side, what are we doing with like the simplest layer? We're simply, we have an affine transformation and then a hyperplane cut. That's an extraordinarily simple to describe locally. You're on one half of the input space or the other half of the input space. Okay, so that's very easy to describe locally. what happens globally is we build up zillions of these cuts in order to form this global tiling. Okay, the trade-off here is that in order to be able to think about our well, in order to be able to build up this high dimensional partition using these simple cuts, which cut all the way across the space, right? All the way across the input space. The price we pay is that there are a lot of unused partition regions that are way off in the corners that are, you know, really, really far from our data manifold. And so I think that the fundamental point is going to be to find a way to analyze, right, what is going on with the partitions that are actually, you know, near the data manifold. So this is, yeah, this to me is a really interesting open question. Hopefully that makes sense.
Can I ask a follow-up to that real quick, please?
Sure.
Is it possible that the widths and the sizes of those partitions near the data manifold can give bounds on what the worst case scenario for things like adversarial examples would be?
Absolutely. I mean, I think this is just this is the kind of direction that we're very interested in. I think that's a great thought.
I have a related question. So
Sure.
in your vector quantization approach, you know, looking at these very nice, visually compelling demonstrations of searching images that are close in this Hamming distance over this manifold that you end up with. Now, my concern though is that I don't think this partition of the space is necessarily unique, and so then, you know, what could I say about these distances that I'm computing? Because then maybe I run it again and the distances are different. Have you guys thought about that, or do you have any comments along those lines?
Great question. Yeah. So just by unique, you mean that if you start back, like they are unique given the trained set of parameters, but you're saying if you relearn the parameters,
Correct.
and it's
Exactly.
still yeah. Again, open question. And I think that the answer to that question could actually also shed a lot of interesting light on like interpretability of a network, for example. Meaning if those distances really are preserved, they really should be preserved, right? Depending on, you know, with you know, two sets of high performing parameters, right, for a network, those distances really should be quite close, the Hamming distances between different data points. And so the question then is what does that tell you about the space between those 2 points, right? And how it is, you know, and how it might be cut up in different ways depending on the different learned parameters, but such that they're both good approximations, right, to the, you know, lying along the geodesic of the data manifold. And I think Randall, actually, I can get to the chat now. Randall has actually jumped in, Randall B, with a you know, some follow on to that.
Thank you. And maybe one last question from the attendees is, if you can elaborate on what you see, what is your vision on what the theory for max-splines approximation can provide to the realm of deep learning, both theoretically as well as improving the performance practically?
Yeah, good point. So we're very interested in both, well, okay, three things that we're very interested in. One is porting you know, approximation theory to this world, right? Because spline approximation in low dimensional spaces using free knot splines or say wavelets, this is very well understood. Porting that to high dimensional spaces using deep nets is something very important, I think. Is being made, right? It's great news. I know I'll say that Ron DeVore, a lot of you know Ron DeVore is working on I'll put in a plug. They're working on an Acta Numerica paper as we speak that should be finished in weeks. So you might want to watch out for that on Ron's website. So that's one direction. The other direction is we're really interested in how this theory can be constructive, right? This is very important to us. But what I mean by that is, we're not just linking deep nets to match filters and then walking away. What we're trying to say is, now that we know this linkage, can we use something from the match filtering world to improve deep nets, right? And I'll just give one example that I didn't have time to show today, and that is that. Okay, so it turns out that deep nets are a signal adaptive matched filter bank based on inner products, and that's an optimal setup for signals, classifying different signals that are corrupted by additive white Gaussian noise. Okay, well, that's cool, but we don't have additive white Gaussian noise in standard, classification problems, telling Ingrid from Anna, for example. So what have people thought about when you have those kind of classification problems? Well, it turns out there's some really interesting empirical results of about 25 years ago that say that for non-Gaussian type problems with correlated noise, something that makes a lot of sense is to build a match filter bank, but constrain the filters to be orthogonal. Okay, turns out it works great. Okay, well, what does that tell us? That tells us that we should build deep nets where when you put in inputs, and you look at the mapping from input to output, that A matrix, those rows should be orthogonal with each other, right? Turns out if you do that, you get just an automatic boost. It's really easy. You just build an orthogonality into the learning, into the loss, and you get a boost, right? And it's almost like a panacea. It gives you like a % improvement in a lot of cases, right? Now, we're not claiming we discovered this, because this idea of orthogonalizing the channels in a deep net was proposed before, right? But it was proposed entirely empirically. Just people had an idea, oh, let's orthogonalize, and wow, it works better, right? And so the hope here is that there will be a whole host of these theoretically or inspired architectural tweaks that will actually improve performance, right? The other one is, don't initialize your RNN with zeros. It's a bad idea. It always works better if you use random initialization. That was not pursued in the RNN community, right? It just works better. How did we come to that idea? By this max-affine spline viewpoint. So hopefully that makes sense.
Yes, absolutely. Thank you. Okay, there are another couple of questions on the chat, but again, to be respectful of people's time zones, let's take the discussion to the happy hour. And again, I encourage everybody, if you want to join us, come over to the other side of the virtual GatherTown environment, and we can keep the discussion there. Richard, again, thank you so much for joining us.
Thank you.
This has been awesome.
Yeah, thanks so much. And just email Randall or me if you have any questions.
Thank you so much, everybody.
Also, don't forget to vote on the posters.
Oh,
yes,
yeah.
Please.